the first law, right? That's what we are going to come to now. But before we do this, since many of you have asked me why some of these are state functions, why some of these are path functions, I've explained in one or two cues. So maybe I could just show you one example. Right? Well, of course, the reason is because all the state functions belong to one state. Right? A state is described by the pressure, temperature, volume. Right? I describe the state of a gas by defining these three things. We have the equation of state. Pressure is equal to function of temperature, volume. Let's say the number of moles of fixed. Right? So if I have defined pressure, temperature, and volume, or if I have defined temperature and volume and I know the equation of state, then I know pressure also. Right? One way or the other. If I have these three variables, then I know that what is the state of the system. If I know what is the state of the system, I also know what's the energy of the system. I also know what's the enthalpy of the system. I also know the entropy. I also know the free energy, the Gibbs free energy, the Helmholtz free energy. Whatever other parameters belong to this state. Right? One state, second state, I know all these things. But what about heat or work? Do these belong to these states? No. They are a consequence of changing from one state to the other. Right? Yeah. You know that the earth is a sphere. Let's say go 10 kilometers south, you could as well go the circumference minus 10 kilometers north and reach the same place. So the work done would depend on what path you take. Right? Also the heat, again, heat is also evolved or taken up in the process. So we cannot associate heat and work with a particular state, but they are consequences of a change in the state. Right? I'll show you one example, a very simple one, a very trivial one, nothing more. Let's say we have some gas over here, okay, and then we apply some external pressure, and compress the gas. So there will be some final external pressure. Okay. I could do it in a variety of ways, right? And by doing it in two different ways, we'll see that how work depends on the path. So let's say, okay, before that, maybe let me tell you, the work is given as minus of P external dV. Yeah, so that brings me to the sign convention also. The sign convention is energy of the system increases, it's positive. Energy of the system decreases, it's negative. So energy pumped into the system is positive energy. Energy taken out of the system is negative energy. If you remember that, you don't make a difference. You don't make any errors. Energy into system, positive. Energy out of system, negative. Which implies that the work done by the system is negative work. So if the gas expands, the volume increases, the work is done by the system to the surroundings, it's negative. If the gas compresses, it's positive. And to make sure that it has a negative sign, when delta V is positive, we put this negative sign over here. Right? So the gas expands, delta V is positive. Putting a negative sign over here, it shows that the sign of work is negative in that case. Okay, So this is minus of P external. That's another thing which people should remember. P external. It's always P external. Okay. Don't make it P internal. It's P internal only in the case when it's a reversible change. And this small cross on top of PW that I put is to indicate that this is not an exact differential. Okay. What it means is that it depends on the path. When I integrate, it depends on the path. In case of volume, I have not put it because the volume depends only on the initial and final volumes. Right? So always work, it depends on the path, it depends on the path. So always it's an inexact differential. Even if I forget to put this, remember that it's an inexact differential. Okay, so now let's take up a process. Let's say we have a P1 V1 to start with, and P external is equal to P1. I compress the gas and bring it to a state P2 V2, and P external is equal to P2. Right. And let's follow two paths. The first part is, let's go from V1 to V2. Okay. Holding the pressure constant. And in the second term, we hold the volume constant and go from P1 to P2. Okay. So this is part 1. Let me just draw it. So let's say we have path 1. Okay, we start from here and we wish to end somewhere over there. So that's P. So it's compression, right? And then that's P2. That's P1. That's V1 and that's V2. Right? It's compression. So that's my initial point over here, and that's my final point over here. So the first path that I wish to take is go from V1 to V2, okay, holding the pressure constant at P1, and then go from P1 to P2 holding the volume constant at V2. And in the other case, I wish to go in this direction first and then hold the pressure constant at P2 and move from V1 to V2. Right. And then it's a 2 minutes job. Let's calculate the work done. So assume the pressure to be constant over there. It's constant. You know, if I integrate this, I get the work done. And since the pressure is held constant, you don't need to worry about it. Okay. So that's the point over there. Right. The first path, the magenta path, let's write the expression for that. The total work done would be equal to integral V1 to V2 If this can be here, then yeah, right. Integral v1 to v2 p1 dv with a minus sign plus another with a minus sign, integral v2 to v2 p, let's assume it's a reversible process, it doesn't matter, actually it doesn't matter whatever it is, times dv, or if you want you can write p external or assume it's a reversible process, doesn't matter. Now if this is the case, there's no work done over here, right? So I can definitely cross it out. So the work done is essentially minus P1 into V2 minus V1. Sorry? So that's bad? Oh, you should just tell me. Which one do you want tippy tippy tap? Okay, let's see. This is good. Is this one good? Black would be too good. Okay, hang on. Let's change it. Just a moment, please. Fine. And in the case of the green one, what we have is work done is equal to minus integral v1 to v1, I guess, p times dv minus integral go from v1 to v2 p2 times dv, right, which is minus p2 times v2 minus v1, and this one goes to 0. And the two pressures are different, so you know that the amount of work done in the two different paths is different, which clearly tells you that work really depends on the path taken, right? Although we are starting from the same initial state and going to the same final state, still doing different amounts of work. Okay. Now, likewise, heat also depends on the path. Okay, and Joule showed this very clearly in 1840, right? There are very many stories about Joule. He had gone on a skiing expedition. If you are interested, you could read up Wiki, but they're very funny stories, so you could read those up. Nani many sonara, huh? But this is about the equivalence of work and heat, right? So he put those weights over there and put a kind of a churner, something that rotates and produces heat. He was inspired from these drilling experiments. So he put that and he calculated what is the amount of work done and what is the amount of heat produced, right? In those mechanical experiments. It seems some. So, and he showed the equivalence of work and heat. Right? Now it so turns out that although work, that is dW and dQ, they are both inexact differential, but if you add them up, then it becomes an exact differential. So these are inexact, but dW plus dQ, the total of it is an exact differential, and we choose to denote this by du. This is essentially the mathematical statement of the first law. This is called the energy. No, this is not energy conservation. Okay. Energy conservation is a corollary of this law. We come to it. This is the original mathematical statement of the first law, the Clausius statement. This is energy. This term U is energy or internal energy, whatever you prefer calling it. In general, just known as energy. The thing is that du of a system, when you come to think of it, we have du of the system is equal to dW plus dQ. But where does this heat come from? Where does this work come from? Right? This comes from the surroundings. Right? So what it says is du of the surroundings is equal to minus of dW plus dQ. Okay. And whatever is not the system is the surrounding. So the total is simply du system plus the change in the surroundings is equal to 0, which is the energy conservation principle. Let me write it in the next line. Okay. So that's your first law, conservation of energy. Delta U of system plus delta U of surrounding is equal to 0. Right. Actually, that's the corollary to the first law. But more often than not, this is what you read as the first law. Energy of the universe is a constant. Right? Okay. Anything that you wish to ask? Okay. Then, yeah. Sorry, can you take that? Okay.
So how necessary is it in our field, like don't we take the systems from the system to the kinetic energy?
Yes. All these molecules have kinetic energy.
Okay.
Yes.
Imagine a container is moving this with heat. Okay, so the system is having the kinetic energy, but not in the form of internal energy. Right? Someday, if I suddenly stop the container moving, the kinetic energy will be converted into internal energy. At the same time, energy is not coming from the surroundings, but it is internally transferring from one form to another. So why don't
But
we keep
oh,
that
in that case, you have to consider largest boundary. Right? Then you have to consider this kinetic energy also.
Yeah, so I'm telling that why don't we consider that all in the Federal's first law?
Very much so. Very much so. Energy can be converted from one form to the other. Right? It's not just for the gas molecules, but for a great energy. But we did have a question like that in one of the majors. Okay. Have you seen that already? Last year major paper? No. Okay. Okay. Now, armed with the first law, let's go on and describe some of the processes that take place. Okay. We'll start with the isothermal gas expansion. Okay. And I don't think I'll be able to finish everything, but let's see. So isothermal gas expansion, which essentially means delta T is 0, right? So let's say we have a gas A, which is at pressure 1, volume 1, temperature. It goes over to gas, still remains A, pressure 2, volume 2, and the same temperature. Right. There are various ways in which this conversion, this transformation can be effected, and an n number of irreversible ways, right? And we should calculate the work done in some of these ways. So let's think about irreversible conversion. So let's say we have this kind of a container, and we have the gas over here at P1 V1, and then I have some stops over here, and the external pressure is 0. Okay, the stops are holding it, but the pressure outside is 0, and this fellow goes all the way to P2 V2. Another set of stops are brought in to hold the gas at that particular position. The pressure outside is still 0. What would happen in this case? So the temperature is the same, right? Temperature is T here, temperature is T here. The work done would be, yeah, it's simply minus integral of P external dV, right? Which is equal to 0. So always expansion against vacuum, the external pressure is 0, and because of that the work done is 0. No doubts about that. Let's see another of these irreversible cases. Okay, let's say we have some gas over here at P1 V1, and then we put a block, right? We apply some mass over there, so the pressure is just force upon area. Let's apply some pressure P2. Okay, and here we have a, so P1 is greater than P2, right? No, P1 is greater than P2, right? So we have some mass that is giving a pressure P2, plus we have these holes over here. So gas can, this cannot push it up, this cannot push it, it's an equilibrium essentially. Right? Now I remove these clamps, and this is still at temperature T. I remove these clamps and go over there. This would just fly off to the position so that now I don't have any clamps. Okay, and this is still P2, so it will equilibrate. Inside it will be P2 and some volume V2. Okay, now we need to calculate what is the amount of work done. Minus P external dV. Now P external is a constant, which is P2 times integral of dV from V1 to V2, right? So the work done is essentially minus P2 times V2 minus V1. It's negative. V2 is larger than V1, so the work done is negative. It's done by the system, on the surroundings, everything is fine, no problems. If I wish to plot this on the PV diagram, how would I do that? Let's say that's my PV diagram, pressure, volume. Okay, so P1 is here, P1 is larger, okay? So P1 is larger, right? Yes? No? P2 is smaller, V1 is small, V2 is large. So we started with P1 V1 and ended at P2 V2. And what is the line that would connect? The line that would connect these 2 points. If I wish to connect it, no, if I just wish to connect that, if I want to draw a line, a smooth curve, what is that curve called? Huh? No, this is the equation of state, right? This is the equation of state of this gas which will connect it, right? So let me draw the equation of state over here. This is something of that sort. Okay. An isotherm at reversible conditions would be in equilibrium with the gas, right? And that's why it lies on the equation of state. But in general, this would be the equation of state that should connect the PV points. What's the work done? Now, the work done is minus P2 times V2 minus V1, which is nothing but this fellow over here, the area of this rectangle. Yes. So if I really want to make a general description of a gas, that is just the equation of state. Right? If I want to say what is the value of pressure of the gas at this particular volume, or what is the volume at this particular pressure, then the only equation that describes is the equation of state. Right? When you make a reversible isotherm, remember it's a reversible isotherm, the gas is in equilibrium with the pressure outside. Yes? That means the gas obeys its own equation of state. And that's when you draw that, that's exactly the equation of state that you draw. Yes? So that's the work done when I do it irreversibly in a single step. Let me break it up into 2 steps. Okay. Let's say that I wish to start from here. Where was it? P1, V1, V2, P2, that's okay. And I want to put a stop somewhere in between, which is P3, V3. So what I'll do is I'll put two of these blocks on top of the piston. Right? I remove one block so that the pressure becomes P3. I remove the second block so that the pressure becomes P2. Right? Is the experiment clear? Yeah. No? So first I had put only one block over here. Here I had put just one block and these two holes. Right? Now I put two blocks. Okay. Let's put a total of P3. Okay. P2 plus something which is equal to P3. A total of that. And then I remove this. And then I get a total pressure of P3. Right? And now I remove the second block so that I get a total pressure of P2. Right? So I do it that way, and what do I find? Well, the expression of work is what we have to write. Yeah, work would be equal to minus. So in the first case, you have external pressure P3, volume going from V1 to V3, minus P3, volume going from V1 to V3. And in the second case, the external pressure is P2, volume going from V3 to V2. Right? That's the total work done. If I draw this work done on the graph, what I find is P3 into V3 minus V1. Oh, that's gone a bit too high. Sorry. That's P3 into V3 minus V1. And let's use another color over here. And I want P2 into V2 minus V3, which is P2 into V2 minus V3. Right? If I compare it with the previous graph, what I see is that I have got this extra region out here. So when I did the work irreversibly in a single step, I got some work. Right? Okay. When I did it completely irreversibly, that is against vacuum, I got zero work. When I did it irreversibly in a single step, I got some work. Irreversibly in two steps, I got more work out of it. The number of steps, if I keep on increasing, I'll get more and more work out of it. You can well imagine that if I have lots of stops over here, I would just get the area under this particular curve as my work, right? Because each time I stop, I'm going to stop at the equilibrium value over here. Yes? Whatever the equation of states, the value of pressure and volume dictated by the equation of state. That is where I'm going to stop. So if I do this infinitesimally, no, the way would be maybe to have a bottle of water and slowly open the tap. So the pressure decreases very slowly, continuously, in a reversible manner, right? And in that case, what I would have is the complete area under this curve. So what we would have is this complete area under the curve. What is says is that maximum amount of work that can be obtained from a system is under reversible conditions, right? Maximum work obtained under reversible conditions. Okay. What would be the work in that case? Right. We are always in equilibrium with gas inside. So the expression for work is minus P. Now P external is equal to pressure of the gas. PdV. If I assume that it's an ideal gas, now of course I don't know the pressure of the gas unless I tell you what kind of a gas it is. If I say it's an ideal gas, then the pressure of this gas would be RT by V times dV. And we can assume that we are dealing with 1 mole, or if you want you can put N also, not a problem. Which gives me yes. I just change V1 by V2 instead of V2 by V2. So I remove the negative sign. That's the maximum amount of work that can be done from the reversible. Going ahead and seeing some of these things. Now let's worry about the internal energy. Oh, we already have.